Hi everyone, this is Jordan from Zama, and I'm part of the machine learning team. Many of us use applications like the Apple Health to track sensitive personal data, like sleep patterns, heart rate, activity levels. But what happens when you want to use a third-party application that offers analysis or insights based on this data? Well, usually you'll be prompted this kind of message, which means you are asked to grant the app full access to your raw health data. What if there was a better way? A way to get valuable insights without exposing your raw data? Instead of having to agree to grant them full permission on this data, you would use a technology called fully homomorphic encryption, which allows computation to be done directly on encrypted data. Today, we will show you how Zama is bringing this capability to iOS using a concept we call the Data Vault. Think of it as a secure guardian of your data for your device. It's the only application that holds the secret keys and the only place where your raw data is ever decrypted. It handles the key management, the encryption request from itself or other apps, and the encryption results. All of applications needing to process your sensitive data must go through the vault and can only ever work with encrypted versions of the data. So we have built a few different applications. One of them is sleep analysis. So when you open the application, you can select encrypted data. So if you pick one, for example, the 7th, you can see the result, the sleep quality, computed in FHE on your encrypted data. Now, the crucial part here is that the application itself, the sleep app we have developed, never has access to the raw sleep data. Everything it handles, the data sent to its server, the result received back, everything is encrypted. Even the visualization you see here is displayed through the secure embedded view management by the Data Vault. The app itself cannot read the clear values being displayed. So, how can you actually build these applications? Well, Zama provides different open source tools you need to do the FHE parts, the encryption, decryption, manage the keys, and etc. And we have built the Swift bindings for TFHERS library, which is built in Rust, and the concrete ML extension, which also has Rust integration, such that it allows you to directly use them into iOS applications. And we provide the build scripts to make this integration process easier. So now let's see how you can actually use all the APIs for FHE within your iOS Swift code. In the repo that we are open sourcing, we have a few different applications. We have the Data Vault here, which is the main app. We have the Elf application. Then we have two quick look applications, which are for secure display within the external applications. And we have an ad targeting application as well. So one thing that we can look at first is in the shared folder, you have APIs that allows you to play with encrypted values. So people that are familiar with TFHRS will see that these FHE uint8, for example, are exactly what we can find in the TFHRS Rust library. You can encrypt them, decrypt them, and play with different API that are directly taken from the TFHRS library. Same goes for the concrete ML. We have different API calls that allow iOS developer to use currently. So now let's see how we can actually use this. The exciting part here is all in the Data Vault. If we go to the Data Vault app and then in the Elf view model, you will see that you have a few different objects that are specific to FHE. So you have the client key, which is the secret key. It's essential for decryption and it must never leave the user's device. So we have the public key, which is used primarily for encryption. It can be shared without compromising the secret key. And then we have the server key. This key is needed by the server to perform FHE computations, like within neural networks, for example, on the encrypted data. The server key does not allow decryption. It's safe to send to the server and share to anyone, basically. So if we check how we actually use this, we go for where we encrypt the data, and that's this. So here is a function, for example, where we will encrypt the data of the night with the sleep stages. The first thing we check is whether the key exists, right? we check the three keys that I just explained. If they don't exist, we just create them. So for example, the client key dot generate will create you a secret key. Now, if we go back to the function that encrypts, once we have created the keys, we're going to use the public key here to encrypt all the example we have and this API coming from TF-HRS. This results in a list of ciphertext, so encrypted data, which is then stored for later access by third-party application like the alpha. And then we have the decryption part, which happens in the data vault again, but this time through the quick look extension. So this is basically where the users can see the decrypted values. So if we look for decrypt here, you'll see that we have FHE uint 16, FHE uint 8, so different kind of data. And depending on what we want to decrypt, we can just call the .decrypt API using the client key, and which return the clear values that are displayed in this quick look extension. So that's about it for this video. All the code for this demo, the Swift binding, TF-HRS, and ConcreteML are open source. We encourage you to explore them. If you want to build your own privacy-preserving application using FHE, if you have any question, please join the conversation on the Zama community forums and Discord. We are excited to help you build the future of private applications. Thanks for watching. Hope you enjoyed the video and see you soon.